Okay, good morning, everyone. Today we are going to hear the final talk of Christian's minicourse about diffeological groupoids. And I hope you're all looking forward to it. And without further ado, let's do some mathematics.
Okay, very good. So I've used the elastic space cliffhanger twice, so finally have to deliver. I've also uploaded the entire lecture notes now, so you can read along. And I cannot possibly write down all the commutative diagrams of an abstract tension functor, which I'll define in a second, and so you can read them. But most of them you will know and are pretty obvious, but then you can read along. Okay, so I've tried to convince you that the left Kahn extension from echo functors on Euclidean space to diffeological space is a really great machine to translate natural constructions on Euclidean spaces, so charts of a manifold, with those to diffeological spaces. And it's kind of analogous to defining something a manifold on a chart and then gluing the charts together to manifold. What do we want to apply this to? So I've also shown that the tangent functor we get by this, the extension, is a pretty reasonable thing. It's the kinetic, it gives the kinetic definition of tangent vectors as equivalence classes of paths that become tangent related on the same set of charts, the same plots. Okay, so what do we want to apply this to now? So now I'm going to remind you what we all have for a tangent for the tangent vector you all know. And I don't even have to now explain the manifolds, but we can do like almost first year calculus and write down what it means, what it does on open subsets of Rn. So, what's the structure we have? So we have an open subset of Rn. Well, the tangent functor of me is space. Let's simply U cross Rn, base point and vector set. Take squares of this. So that's now the base point of the double tangent funnel. The vectors with respect to the second parameter, if you think of these guys here as parameterized by families in two parameters, and then differentiation twice. And we also have something that, okay, so I don't think there's canonical notation for the fiber product of the tangent funnel or any overcategory. Define. That's the notation for k copies of tangent vectors at the same point. And we really just need to write it down. T2 of u, which is in this local chart, it's just one base point vectors. So, well, then the transformation maps, the applying the tangent functors to smooth maps, you know how this works. And so what do we have as structure? So we have one projection that maps u. And I put an index for the first differentiation, so first the time usually for just the tangent funnel. So that's point u, zero section. U. Well, so I want to stick to specific order. Confuse you later. So the addition of that lives on that twofold fiber product. It takes two vectors of the same base point. So u1, v1, and to u. Inverse, but then this is a group structure, so that's just a property. Maybe I don't need to write this down. That's it's unique, but it's also natural. And then perhaps one interesting ones. I'm vertical. Let's call this lambda u and uses that I can identify the tangent vectors, the fibers of the tangent of that vector bundle, tangent of the vector bundle. So maps u, u1, 2, 0, 0, 1. And I have a flip, which exchanges the differentiation. So if you take the tangent function twice, which changes the parameter differentiation with respect to the parameters. So this goes t from t to square root to square root u. Now I exchange 1 and 2. 2. U21 is U12, lemma Schwartz, I think. Is this what it's called? Okay. Okay, and now I can, out of those, I can construct actually a pretty rich structure of more natural transformations that you may not have thought of. So first, what's clear that the tau u is a symmetric structure on the powers of the tangent function. So there are more and more parameters which parameterize higher tangent vectors, then I can exchange all the parameters. So I get an action of the symmetric structure on Sn, on Tn, for example. Less known is that, for example, I can, okay, so this is a quiz for you. So for the differentials, you've known this guy, the tangent vector, since your, I don't know, academic childhood. So who knows that T is a monad? Okay, so I have a commutative monoid structure on T in the monoid of endomorphisms, endofunctors, sorry. And the algebras of the monad is an interesting class of singular foliations. Or did you know that the powers of the tangent functor have a cosimplicial structure? This is suggested by the indices. Actually, if I start with 0, 1, 0, 1, and I keep going, then you will see that the indices are labeled by all non-trivial subsimplices of the standard simplex, and then you can kind of start to guess how this works. Okay, so there's some things I also learned about this functor, who I thought I knew everything about already. Good. So now Rositzky in '84, he captured the essential structure of the tangent functor in the notion of abstract definition, concept of the abstract tangent functor, and this is what I cannot possibly write down completely, but most of the properties you can really read off from these maps here. So definition. On some manifold, sorry, so on some category is endofunctor. So think diffeological spaces later, together with the natural transformations I wrote down here. So let's call the elements of the X. Section. Well, yeah, inverse is explicit from the axioms. Vertically lift. Flip. A whole bunch of, that's a pretty rich structure, a whole bunch of axioms satisfied. So plus a long list axioms. And most of the axioms are given by commutative diagrams in natural transformations. So consisting of a, well, not large, but a number of commutative diagrams for example, most of these transformations are bundle maps, so they leave the base point. Right, then, for example, plus u plus x, sorry, 0 x and this. So, like really, that guy here is an group object in, well, the bundle category. It's also supposed to be bundle maps, so in the over category C over X. Okay, now you can spell out the diagrams, the usual commutativity, then for the abelianess you need the flip and so on. Okay, so that's the things you can look up in the notes, and most of them you will say, duh, yes, of course. Okay. And not yes.
What is the index to X?
It's the same as this. It's just like universal that eats u or x or anything. Okay, so it's
the full.
Yes, so it's the fiber product. It means, is there a standard notation for this? I don't think so.
Yeah, but in this abstract.
Yes, in this abstract setting, it's the same. It's a pullback over this, the bundle projection pi. Okay. Right, so they're the commutative diagram type axioms. Then, of course, for all this to make sense, sorry, I'm going a bit backwards, but I want to get this off my chest. That's the more or less obvious ones. Then, well, it's not going to be an issue in diffeological spaces when we start. So these fiber products Janus asked about, they should certainly be required to exist. This should be the first axiom for all this to make sense. That's doubly more interesting ones exist and commute with itself. So like for this fiber product, the tangent bundle projection behaves like a subversion. And here's perhaps the most interesting one. Next, following diagram. We can read this off. Here, so lift here really lifts this tangent vector at the 0 section of the tangent bundle, and then puts this the component U1 in vertical direction of the second tangent bundle. So if I let's go back for once. Okay. So if I apply here projection of these two guys here, U1 to U1 and U2, they're 0. So this means that 0 And the requirement now is that this is a program. Yes, that this is a program. It's also a push out, so you can read this as use it as a short exact sequence of vector bundles. Okay, so this is the projection that inserts the kernel of this projection, which is the vertical part of the tangent bundle. The splitting of these would be a connection, so a horizontal lift of a connection, or connection one form, if you split on the other side. Okay.
Yeah.
Yes, of course.
So you mentioned the addition along the fibers.
Yes.
Basically. But yeah, that's a bit of that. But you didn't mention multiplication by scalars. Is that because it follows automatically, or?
That's an excellent question. On TU, we have multiplication by scalars. On diffeological space, we have it too. It's not part of the general definition because most categories won't contain R as an object. Right? So that's why it was dropped. We will have it, but it's not. So, like, this, for example, works for the category B groups. And that's a tangent category, and that has such a structure where you have Z multiplication and not R. And so I don't have a life as a secret computer scientist, but the people who are working on this now, and whose papers I read, they are what I would call categorical computer scientists or computer scientific category theorists, and not people who use this in connection with computation theory or algorithms. Okay, and they don't like they don't want to have, for example, R multiplication now. R doesn't exist. Okay, good. So this is, I just give you a flavor. You can look up the entire diagrams. It's a long list. Also, I've already consolidated a few things that in truth more diagrams, but if I say that tau is a Noidal structure on the tangent functor and explain what this means, you can also spell this again out in terms of diagrams, but essentially it's just the Young-Baxter, like the braid relations, and that tau squared is the identity. Okay, good. So a category, so C. Good. So now, finally, we come to elastic spaces. Once we have established that these elastic spaces are a tangent category, I will explain you why this is great for doing differential calculus. Have this tangent structure. Okay, so now we want to throw our extension machine to all the structure. So one nice thing is, so we've already seen the tangent diffeological space is just the extension. We've also stated that the powers that appear T squared, for example, is the same thing as the extension of the powers. So this factor is monoidal, and that's important for our translation. And then we have that's fine. Powers are fine. And so whenever we have diagrams that involve the powers of T and some natural transformations, they're going to map from commutative diagrams in the Euclidean spaces, the baby stuff here, to commutative diagrams on diffeological spaces. So, so the functors are pi x, 0x, inverse, and set lambda, vertical lift tau, so map. So diagrams, all the axioms diagrams of magic transformations diagrams. And just in the bulk of the axioms you have, this takes care of 80% of the axioms automatically. So this is why I think it's really helpful. But where you see there's a but coming, the Left-hand extension does not commute with limits. So it does not commute with the fiber products that appear in the fiber product of several tangent vectors that are the domain, two tangent vectors are the domain of addition. So this is not limits. And therefore I have to wait to work. So you see that this creates the problem with addition. So instead, we use a new functor that appears here. We call this theta sub k. That's the kind of extension of sub k. And using the same letters here for the P on a Euclidean space, diffeological space, and then also put a hat on it and just treat clutter the notation. So, so I have this guy. And I still have the projections from tk to all factors of k, which become the projections from theta k to, I also have k projections, which means I still have a map, natural map of factors from pkx to tkx, where x is now the honest fiber product of the tangent factor over x. It's called this small theta k. But now this is not generally an isomorphism, and the addition in spaces, well, it's a factor from t sub 2 to t is going to be mapped to and from theta sub 2 of x to tx. And I have a map like this, and I don't get a map. This is generally not surjective or injective. I get a map from T. I don't get a map from T2 to Tx. I tried to save this, by working in spans, but it just doesn't, at the end of the day, it didn't work. I've tried this for a long time to go into category spans instead. That's a span of addition, if you want. Substitution for addition. Okay, so that's the issue. And there are the diagrams that involve this T sub k, like this pullback diagram, where also instead of T2, T sub 2, the phi product, the theta 2 will appear, and if I replace this naively with the T sub 2, the diagram won't even be conditional anymore. Okay, so that's the things that give me problems. And now the question is, what is the right condition that ensures, well, first, that you have an addition, but also that the whole rest of this huge number of axioms is satisfied. And the upshot is, logical space is called if but for the addition you would need that the map from theta 2 to T2 down here would be an isomorphism, but then for associativity you already need T3, and for higher, like for higher things like the domains in which you want to define forms, TK, K forms, maps out of TK, you need also for all Ks. And then I've tried a long time to prove that this induces that this works for X. And so it also works for the tangent diffeological space of X. That's not true. So we need to add that this is ISO for our. Okay, now I've promised to explain why I call this elastic. So what's the terminology? Well, think of it like this. So instead of charts or models, we have just all these plots that are somehow mapped to the diffeological space. And if you're in infinite dimensional spaces, like function spaces, there's nothing ever going to be surjective, right? Because you have open subsets of UNs, and you map them into a huge space, so they're just going to lie in there somehow. And so what is the theta K? It's this. So, and versus so these tuples of tangent vectors at the same point. And these will be, after taking the co-limit, will be tuples, k tuples of tangent vectors at the same point that live on the same plot, live on the same surrogate chart that we have. So the question now is to see if something is elastic is given k vectors here, can I represent them uniquely on such a chart up here? Or uniquely, that's not the right term because there's lots of equivalence classes, lots of equivalences up there. So the chart is not uniquely, but if I fix the chart, it should be unique. A chart, I keep saying chart, unique plot. Okay, so geometrically, what does this mean? So here's my diffeological space. Well, so if I have a tangent vector, I can always represent this pi path. So I think of this in terms of you're giving me an infinitesimal direction, and I somehow have something I can stretch out in the space, like a little rubber band that gives me that path that's stretched out along this tangent direction. Okay, so I would call this one elastic. So elastic in one direction, give me a vector, I can do this. Now, if I have a second one, so every diffeological space, as I've shown, is one elastic in that sense. But if I have a second vector here, can I find a plot where this looks like this? Sorry, that's a very tangent. Where I can simultaneously stretch out my diffeological space in two given directions, infinitesimal directions. And now this is not supposed to be two-dimensional. That's not a chart. It looks like the diagram is this. It just lies in there somehow. This is like gazillion dimensional here. And so if I have a third one, I also want to stretch it out in a third direction. So that's a really bad picture. Some kind of plot, three-dimensional plot that sits in here. And so this is my intuition for what you do on plots instead of charts. In this space, you pull it out a bit in these directions. There's nothing needs to like be local isomorphism or something, not at all.
May I ask something?
Yes.
Sorry, so this is probably just coming up this, as one of the next examples or something. Is this a condition you can check for, let's say, non-trivial examples? I'm asking because there's, especially when it comes to tangent spaces for diffeological spaces, they're, my impression is that they're notoriously ill-behaved and difficult. At least when I recall some works where people have tried, for example, to define a diffeological version of a Lie group or something, and to check anything that was next to impossible, at least what I recall from their papers.
It's a pretty nice category. I will state this now, give you examples, list of examples, okay? Yes, answering your question is the next on my item on my to-do list for this talk. Okay, so first, let me, so this is I just want to explain my terminology on geometric addition on this.
But this was only for algebra 0. No?
Yes, for algebra 0, and now we additionally require that the tangent guys still have this property. That's exactly true. And
So that you have a tangent.
yes, and I need to find weird counterexamples. I can maybe tell you in the break, because I thought this should be possible, but it's possible that the space has this property, but the tangent space does not. And you have to do this counterexample game, which is.
Excuse me, there's a
Yes.
There's a question from Joel. He's asking if being elastic implies that the tangent spaces are actually vector spaces.
Yes.
Thank you.
But that the tangent fibers are vector spaces. There's no local trivializations whatsoever.
There's also another question. They cannot read what's the first word on the last line on the left blackboard. Is it ISO?
So,
Yeah, thank you.
okay. That's nice morphism.
For example, a manifold with boundary would not be allowed.
Yes. Okay. Let's get to example. Let me first state something because I need this for the examples. So, of course, there's a price to be paid. This can't be as convenient as the category of diffeological spaces anymore. But here's a few things that still work. So, elastic spaces goes under operations. Arbitrary co-products. Surprise. And retracts. Not so hard to show. Retracts isomorphisms are stable under retracts, and that's all you need. Yeah. So this brings me to examples. If the examples I care for weren't in this list, then I would have that in this. Okay, so here's my list. So I explain the examples in more detail in the notes, and sometimes you have to justify that they're elastic. It's not necessarily easy. So first of all, of course, manifolds. Then you have to check that diffeologically this is a retract. Both maps are diffeologically smooth. And this endpoint here is just a resting point that forces derivatives all to be zero, and that that there's no problem with x. Look it up in the notes. I'm trying to. It's a tiny bit of analysis. So this means by that statement that this is elastic. It also means that all products.
The R should be
For goodness, text. Oh, that's right. Okay. So the half space, closed half line is elastic, and therefore what's you can go further now if you have a corner like this. Such a space, you can squeeze it to cusp. Like y cubed equals x squared kind of cusp, for example. And again, you can check that this is elastic, that this is retract. And so this is also, oh, I drew it the other way. So this is a retract of that. So this is also then you can come up with more examples. So
it's elastic with particular diffeologies that basically break all tangent vectors to zero.
it really is the subspace diffeology in this case of that of our n. It's a very natural. There's nothing weird happening here.
So what are the fibers of the boundary?
Fibers, the tangent fibers are here, are 2 in here, and 0 here. The same here.
Also 0 before.
Yes, because think of the tangent space represented by smooth paths. Any path that stays in here and passes through this will have 0 derivative, 0 velocity here. So that's just it's not that deep, and you just have to get used to the fact that you don't have local triviality, and that the other models for tangent spaces of manifolds with boundary, that's very similar. It's great. I'm just different options, okay, to do this. But here it just comes out that this is fine. Okay? So you have stuff like this, or things like this. Or you can also have stuff like this. But now different angles. Oh, this should be the same. The subspace diffeology, just there being a corner means it all has to go, the vectors have to be 0, so the tangent space is 0, that's fine, that's the vector space, here it's R, and so on. Okay. So these are fine.
So just another clarification. If you iterate the tangent function as you were doing before,
Yes.
so how does the counting go? I mean, like, you have tangent vectors approaching the boundary where some components have to vanish. They are still approaching that at some finite rate, so maybe you take an extra direction in that figure.
Generally, that can be a difficult problem, but here you really have sort of the vertical direction, which is the fiber direction, and you have horizontal ones. And in that case, it really sort of adds up. Okay? But you can have more fancy examples. Right? So here, that's your base space. You take the tangent bundle of this, so that it has R here and 0 here collapses. And now you want to know, if I take T of that, what is the tangent fiber here? Well, it's still 0 in that direction, but it's also the 0 fiber, so all the vertical paths are also 0, so this is going to stay 0. Here it's going to be R2. You can fidget around with this and come up with one more funny examples. I haven't fully explored this with the singularities and subspaces, but let me.
May I ask a question here? Because it fits exactly. For some applications, you would like to have tangent vectors which point into the interior.
Yes.
And then you could look at diffeological spaces where the plots are only open subsets in quadrants. And then you would have these. Maybe this would be kind of diffeological spaces with boundary. I mean, very often you need vectors or vector fields on a quadrant, for example, which point into the interior in order to make some constructions working.
Yes, this is certainly not something that works for applications. So of course, if you have the half plane, you can equip it naturally with the subspace diffeology. There, the tangent vectors have to be 0 at the boundary, strictly 0. But you can also take the folding map, the Z2 action on R2, and equip this with the quotient diffeology. And there you would have these inward pointing arrows, but this wouldn't be elastic anymore. Okay? All I'm saying is that this works for what I want to do with it. I completely agree. That's really not something that is, is good for all situations. In fact, the singularities is not sort of my main concern. Next example is function spaces. C, infinity, and sections. They're elastic. And since we're in this workshop on infinite dimensional stuff, that I think is a good thing. That's mostly what I'm doing this for. So this just fits the things I have in mind to do. At the end of the day, I want to do kind of a considerable Blohmann geometric approach to deformation theory using this, applying to higher diffeological groupoids. But that's a long program. I can't say much about today. Yes?
Yeah.
Progress.
So I wanted to ask what you mean exactly by diffract, and there must be some smoothness condition there, because you said that this last drawing on the right, the one just behind you,
Yeah.
That is elastic.
Yes.
But if you take the union of the axes,
That's not
yes,
elastic.
that's not elastic. So
Okay.
it matters if the lines are in one different direction.
Yeah. So here, another example would be something like this, where you force the paths to all be tangent to the same thing, and you still have R. But here's an example that's not elastic. So this point, that's literally a cone, not a vector space, a tangent space. Or, as you said, this cross of X is not elastic. That's not okay. The tangent directions are not a vector space here.
So when you write retract there, you mean what? Smooth deformation retract?
No, nothing deformation, just categorically, otherwise it would work. It's just a smooth map with the left inverse. That's it. It's really like a nice and relatively weak condition. Oh, that would be much stronger. Okay.
Excuse me, there are a couple of questions in the chat. There's one question from Alexander Schmedding. If the manifold means finite dimensional manifold.
Yes.
And there's a question from Tobias Diaz. Maybe he can ask it himself because I don't know the details.
Yeah. Yes, my question was also about the function spaces. So what are your assumptions about the manifolds? Are they kind of like allowed to have boundaries? That's a bit like similar, like in spirit of what Peter Micho asked. So if I have a manifold with boundaries which come out naturally in field theory, right? And then you would like to have kind of like vector fields that point inwards, or kind of like to model boundary conditions of your PDEs that you're studying. Kind of like, are these also examples if you have?
Yes, I don't know exactly. I mean, I can say from the top of my head, if n has a boundary, the target, then the retract will induce a retract. And so the boundary thing came from products and retracts. So if I have products here and retracts here, this would be fine mapping into it. Mapping out of it, it doesn't seem fine. So I would guess, okay, I don't have a fixed answer to this, that in this situation, n can have boundaries, cusps, and everything you have here. But this not.
Okay,
Let me put this on my to-do list. Okay, that's really lots of interesting questions like this that appear immediately, and you really come up with a long list of things you want to check.
But if n has boundaries, then the tangent space would be also then tangent to the boundary, right? Like they wouldn't go like have inverts quantity.
So the reflection type boundary, like cutting in the box, wouldn't work.
Okay, good, thanks.
So that's maybe not satisfactory, but that was also kind of similar to what Peter asked. Okay, good. So why do you like this? So here's now the big did I say this already? Has some number. Let's check that here. True. So that's the thing that really took a while to figure out. Category. Spaces is a tangent or with a natural tangent function. And I really need all the nice categorical properties of diffeological space I told you about at the beginning. And it's really, it's really a long proof and technical. And the most difficult part is to have this that this one diagram which is supposed to be pullback to show that this is a pullback, because that's not something that comes out of your machine. Okay, good, but it's true, and so this is very nice. So it's also, the questions that were asked, it's a pretty nice category, it's a pretty strong condition. So you would certainly not be in this, this elastic, happy world where all weird things still work out. So that's certainly the price we'll have to pay. But what I want to do is I want to, at the end of the day, I want to have something like a Lie theory for differential groupoids. And for this, I need quite a few things. And the tangent factor is exactly what we need for this factor of these properties. And that's what Laurie Kadian will tell you something about this afternoon from a PhD thesis. Okay, so here, another explanation what's good about it from a different angle, what's good about elastic spaces, and what's actually was one of the reasons I decided to look into this, is the following. So, so I promise that out of this, I get a full calculus on elastic spaces. So what is if you don't care about this kind of extension and everything? So what is the problem? So there are two ways of defining differential forms. Natural definitions of differential forms and diffeological spaces. So two definitions of forms. The one that's pretty canonical and everybody agrees that it's great is by time extension of the round functor meaning omega of x is colimit of omega u for omegas. So what is a form in here? It's a family of forms. Oh, wait, I need That's right. Sorry, because it's a contrary fund, it didn't change something. I don't think so.
Can I ask a question? My question is some examples about a sheaf and ether space is are not the example or not.
So I said the space of sections of a smooth fiber bundle is an example for elastic space. The construction is local, so this works nicely for sheaves. It also works nicely for pro-manifolds, for example, like the infinite jet bundle. And so for a smooth sheaf, in that sense, that one is represented by really by a smooth fiber bundle that works. But certainly you cannot do like Italy space constructions or something this way. I think actually once you go sort of to underlying like just a topological structure for your sheaves, you will lose everything. So the tangent functor on topological space, the tangent fibers are 0. Okay. So here,
thank you.
What's a form? It's a family of actual forms on every domain of the plots, such such that if you have plots like this, so two plots U, V, X, and F. So an element in here is a family of forms alpha, again, omega, Q for all these plots, such that let's call this alpha P, alpha sub P, so that alpha P is F pull back. That's an ordinary smooth map of alpha Q. And this is pretty canonical, so that's a nice definition. And it comes with, since I took the bit in complexes, comes with the Durand differential, and it's just applying the Durand differential to every guy here. Yeah, and you see this is nice because it commutes with Bomax. Okay, so that's how it looks. So that is good. That definition is good for a Durand differential. So what else do we need for a Cartan calculus in a derivative? And this is simply not defined here. And you can check it and you can show that generally there is no operation and it's unfixable. You cannot insert vector fields into these forms that would give you a well-defined thing. I mean, I tried for a long time. You can view the pairing as natural transformation, blah, 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 and then at the end you still find it fails. Right? So the second definition forms is a fiberwise smooth map. Okay, it's a K form. Now this guy obviously comes with the inner derivative. It's just precomposition. You just insert the vector field in one of the slots here of the fiber product, and that eats away one of the arguments and turns the K, like a K form, to K-1 form.
I apologize. It's very active in the chat today. There is another question from Peter Micher. If he could just unmute himself and ask it.
So the question is, what about vector fields?
Vector fields with respect to vector fields simply sections of that's the good notion. And now the next question
flows. What about flows?
This integration, I can say at this point anything about this setting. For this, it's really too general. Like I can put pretty crazy stuff in here. I'm sorry that of course, this is on my list of things, integration problems, but at this point I haven't like really thought about this. I think it might actually be quite a number of additional assumptions for flows to exist. That's just my hunch. Okay, but so now we have the ground differential, vector fields, inner derivative, but they don't match up these forms. So here's more or less an observation. So the two forms coincide. The theta that map that k of x to t k of x is a nice. So it's for k forms. So for all k, you need this to get for all forms. So this again tells you that would have been another way of coming up with the elasticity condition. Here, just for the vector space of forms, an easier one, but now if you think of the full ground calculus, we also have to include the tangent condition that this works for all tangent diffeological spaces. Okay? So this is another support for why you need this condition for things to work out nicely. So now something that I mentioned at the beginning when we derive the Lie bracket of diffeomorphism groups, there we used, and we have to think about whether for necessity or for convenience, that you have a faithful representation of vector fields on the space of functions of n for diffeomorphism. So do you really need this? The answer is no. So here's how you can define the bracket. Okay, let me make sure that I don't mess this up. So here's the definition of the Lie bracket. So that's a long, now you need all the structure you have. So you take the point x, take it twice with the diagonal map. Now you apply v, the vector field, so v w maps x tx on the first and w on the second. This gives you something tx, since it's all bundle maps, it's really tx higher product. Then you need another time now on tx, so you need the t of the end up in t squared x over x squared x. We've already used here that the tangent factor commutes with these pullbacks. I'm running out of space. Now you apply minus the inverse on the second one. Commutate that. Sorry, I'm going in circles. Now you add, there's something in t squared x. Okay, so you get a map of x to t squared x. That's not what you want yet. So now you're checking that now the map lies in the kernel, has values in the kernel of that projection that appeared in that pullback diagram. So this was the projection on, so this was I tx. And so here is, so you map, so this map, let's call it beta. So beta, BW is a map from x to this, to that map here that factors this. This means that it has values in the kernel, so the vertical part. And now the axiom was this here with the vertical lift is a pullback. So this means you get a unique morphism here. And that guy here is what we call the bracket. And now you have coherence problems. You have to show that this bracket you define this way, it satisfies Jacobi. So the story of this is Rositzky stated it, never gave a proof because it was a complicated thing. Then people in the 2010s started to be interested in this again. And they sent an email to Rositzky, what's about the proof. He sent back 70 pages in Czech of notes. And they mentioned this in the paper, but they obviously didn't give up. And I think it was Cochran Padua, and a few years later, they've sort of bit the bullet and written this really long paper with lots of coherence diagrams and stuff. And they checked it is indeed actually bracket satisfaction code. But this is nothing you see, okay? There's, if you take sort of the categorical things seriously, that, you know, everything's, when you work with natural transformations and something is equal, you really mean up to isomorphism, natural equivalences of natural transformations. And then you have to ask can I get away with treating this as equalities, or do I have coherence problems? Okay, good. So now, yeah, I should probably wrap this up. So this is the bracket. The theorem is, I'm just going to say in words, it's also on the paper. The tangent functor, and then in addition, in that specific situation of classic space, have the R multiplication, gives you a full-fledged Grothan calculus with vector fields, differential forms, Gram differential, inner derivatives, and lead derivatives defined by the magic formula. That satisfies the usual relations. Okay, so what is this good for now? Let's now, can I have like 3 more minutes? And we already had kind of a discussion in the talk. Okay, thanks. So this definition. Elastic logical point is a point external logical spaces, and its nerve is all elastic such that GK is elastic. Okay. And then once you have this, you can, and it's going to be explained in the talk for Canadian. You can construct an infinitesimal object a higher logical. Well, sorry. Here I set it for actual groupoid. I realized I want the nerve, the simplicity of logical space to be elastic. So you're guessing so if you know I'm a higher person, so I want this to work for higher groupoids as well. So I put this in parentheses, it works for higher situations too. The algebroid, that's just algebroid. Generalizing the Chivera construction to actually generalizes to arbitrary tangent vectors. If you know the Chivera construction. Anyway, if you've not replaced by some known construction. And that's what we wanted. And so the state of affairs is you can express this shear construction in terms of a certain end of powers of the tangent functor. I told you it's a co-simplicial structure applied to the simplicial, diffeological, elastic diffeological space, the nerve. And this gives us this infinitesimal object. And so we're checking that I'm pretty sure that this reproduces the algebroids in the usual situation and hide the algebroids. We just plug in ordinary manifolds. And then we have a construction that works generally for elastic diffeological spaces. We're thinking of deformations, so families in diffeological moduli spaces of structures. Okay, so that's the end goal, which is still a bit far out. Okay, thank you.
Thank you very much, Christian, for this nice talk. Because we're a little bit over time, let me ask for online questions first.
There are 2 online questions from Peter Micher and Alexander Schmedding, and also from Joel now. So if they could just ask them in this order.
Yeah, thank you. My question is very short. What about the cotangent bundle? Is this elastic again? And do you have a symplectic structure there?
I don't know. So for function spaces, Annika has defined the cotangent bundle, but this I haven't looked at yet, and I'm not sure this. I'm not sure what the good. Well, I think it should not be so bad. So since the cotangent bundle has I guess yes, okay, but I can't really say. So since the forms and the differential forms by extending the Durand functor and the maps out of decay coincide, I can really go to like Iglesias Seymour's book where he, does a lot with these kind of differential forms of tangent bundles, and some of my hunch is that it should work, but I don't know. I put this in my to-do list. Thank you.
What was the next one?
So Alexander Schmedding?
Yeah, I guess that was me. Hi. So I guess it's more 2 comments basically. So it seems, or perhaps the first one could be phrased also as a question. It seems to me that these elastic spaces are doing something. So you're restricting again sort of what the pathologies you can have in the diffeological category. That's to something which is more manageable and then does your bidding basically. That's at least the impression I got now from the elastic diffeological spaces. So that's okay. It's now not a question; it's more a comment. And the second comment I wanted to make is since you now define diffeological groupoids internal to the elastic ones and get algebroids out of this, I just wanted to ask whether you're aware of. So there's an older work by Martin Laubinger. He is, I guess it's his, if I'm correct, it was his PhD thesis, where he's trying to construct diffeological Lie groups. And his main problem was that he had some quite complicated conditions for when he wanted to define the Lie algebra associated to a diffeological Lie group. And so, I mean, Martin was getting his PhD at the same place where I got my PhD, and if I remember it correctly, he could basically never check his complicated conditions beyond the trivial examples where you already had a stronger structure, right? Like, for example, an infinite dimensional Lie group structure, either in the convenience setting or in the Bastiani setting or whatever. And I just wondered whether this concept of elastical spaces would be elastical diffeological spaces would be the right setting also to define some. I mean, if you're now doing something which is already more complicated, right? So you're doing diffeological groupoids, and so the
answer is unequivocally yes. And since I ran out of time, I just skipped my most important example. So the most important class of examples is the following. every diffeological group is elastic. That's a theorem. That's not an observation thing. You need to jump through some hoops. So for groups, for any group, any diffeological group, this works.
Mm-hmm.
So the answer is yes. There's no problem whatsoever. You can take simply right-and-brain vector fields.
Okay. I mean, I don't recall what really was the problem with. So he probably wanted to also. I think it was defining the bracket, but I'm not so sure after all these years. So it might. I mean, that the thesis is around 2011, I think, something like this, so 10 years ago. And it might also be that there was some connected issue with sort of making Lie theory work for these things and not just defining a bracket. I don't recall that. It's just it would just be interesting to see how whatever he has been doing is faring in this with this elastical technology we have.
This I don't know, but as I mentioned, showing that the Lie bracket is a Lie bracket is very involved. It's not something you just see.
Yeah.
That could easily happen that you just don't manage to prove that.
Yeah, that might very well be. Okay, thanks.
Sure.
All right, I guess it's my turn. So this is kind of a technical question, but are the tangent bundle projections local subductions?
Yeah, local subductions. I've thought about this a long time. Also, people often believe that local subductions are a good surrogate for submersions.
Yeah, me included.
And I'm not even sure that is true. And I also don't know whether the bundle projections are local subductions. And I think I can construct counterexamples.
Okay.
And sure, but this is on my list. Please, if you really care about it, maybe bug me again about this, and then I think about it again. But I've tried for the longest time to show this and or show counterexamples and see whether I could have weaker set of axioms.
Mm-hmm. And do you have any any knowledge about the behavior of the dimension of this tangent space of these tangent fibers? Are they locally bounded below or something like that?
In the examples, the subspace examples, they are. But I'm not sure this is always true. I haven't worked much with the topology induced by the diffeology to answer these kind of questions. I've tried a bit, but it's also on my list.
Yeah.
This I don't know. You just seen in the examples I gave that that's true.
Yeah.
But otherwise, once you go to infinite dimension, there's really crazy things you can construct. So since every diffeological group is elastic, every diffeological vector space is elastic. And now you probably know that there are really crazy examples with weird properties. So this I'm not entirely sure. You could take R copies of R, something like this, with the product diffeology. That's a bit weird. But
yeah. I guess I was thinking of the examples where the dimension is bounded.
Yeah, that of course is not a good example, but I mean examples you build out of things like this.
Yeah.
Behave weirdly.
All right, one more question that is either a quick answer or another thing on your list of things to check. Do you happen to know if, you wrote about the fiber products of the fiber products occurring in the composable arrows for groupoids? You wrote that the composable arrows have to be internal to the elastic setting. Do you know if fiber products along local subductions of elastic things are elastic?
Joe, you're asking all the right questions. Of course, I try to show, as you can imagine, that the tangent bundle projection is a local subduction, and that it's true that a fiber product of over a locus subduction commutes with the tangent functor. And I don't even think that this is true anymore. I thought this must be true. And then I more and more came to the conclusion that you're really using, for this, to show this with submersions, using the local structure theorem for submersions, that it's really product space for this to work out. This is not a proof, okay? This is just, I'm just acknowledging that this is a very good question, and I've asked it myself, and my hunch, my current hunch is that this is not true. That this, that the subductions are not, local subductions are not good enough for this. They don't, in this respect, they don't behave like submersions, but maybe I've just missed this. I can't give you like a clear answer. That's good.
Okay. All right, thanks.
Okay, that was it for the online questions. Okay, then we go to break now, and everyone who has like other questions can just ask them one break. And when will we start again?
5 minutes.
Oh, goodness.
In 5 minutes. Okay, we will start again in 5 minutes.
Well, this was the last lecture of this mini course, right?
The application.
I would also like to thank the speaker for this lovely mini course, and as you know, judging from all the questions, it has been very successful.
Thanks, Lily. That's very kind of you.